Ian Stuart, welcome to Wood 40.
Thank you, Sandra. It's great to be here.
Yes, thank you so much for coming out to engage this discovery lab that we're doing with scientists. And it's a great pleasure to have you in particular because you're so into engaging kids. So tell me a little bit about your background. Where did that start? Were you, like, I know you're a teacher?
Yeah, I was a kid once, actually.
Exactly, you're a kid once. Where did that interest in teaching and specifically in chemistry started for you?
I think I discovered chemistry in high school. I was one of the few students who actually enjoyed chemistry at high school. And I think it's because I was brought up out west in the outback, where there was very little understanding. Everything was concrete in the outback. Whereas when we started learning about chemistry in high school, I discovered a microscopic world, that everything is made up of invisibly tiny things, and that was a mind blow for me. I just didn't see it coming.
Oh wow! So do you wish that you would have discovered that earlier in your life?
Well, I never sort of thought about that until later, when I started talking to my son, who was 7 years old, and I'd already had an understanding of this, and we talked about it, and he could pick it up really quickly. So I thought, well, this is the time to teach it.
And as a child, did you have interests in science per se, or any like the natural world? Like, what were you like as a child?
Once again, when I got into high school, I started blowing things up, as most chemistry obsessed students do. And I had a chemistry lab. My brother was an industrial chemist, and he probably had an effect on me too. That there was that kind of transfer of information and understanding. And he used to bring home old, partially broken equipment, and I could resource my lab with all of this extraordinary glassware and Bunsen burners and stuff like that. I mean, it was a dream for a high school kid.
That sounds amazing. So what year would that have been in?
I would have been 13 at that age. I was making sort of working with concentrated sulfuric acid and making chlorine gas and doing really dangerous things that we couldn't do even as high school teachers now in a lab. So there was the Wild West then.
And you were out in the outback of Queensland?
I was in Brisbane by that stage.
Yeah. Cool. And the beauty of that, I guess, is that inquisitive nature that you had, and this sort of no huge level of resistance to learn despite of it being dangerous. That's sort of something that kids and teenagers still retain, and as adults...
Well, because it was dangerous, I think rather than despite of it. But there was a thrill factor there. But also, it wasn't just the spectacularness of it. It was the cognitive element too, that you could understand that there's something microscopic happening here, as well as things being blown up that you could see and feel and touch. And that's what that coupling of a modelling of what's going on and seeing it really happen in our physical world, that's what got me.
How did your parents feel about having your own lab at that age and exploding things?
That's a good question. That's a good question. I never really asked them, and they didn't. They just took it. They were very tolerant parents, I have to say. Yeah,
beautiful.
Yeah.
Did they encourage you in the science area, or?
I think it was that was something that they hadn't had any background or experience of. So they weren't indifferent, but it was just a different world for them. They didn't have the opportunity. I was brought up in the era when the post-Sputnik era, when Australia invested a lot of money in science education, and so it captured a lot of the imagination of students and teachers for an historic period of time, and that the previous generation missed out on that completely. So I think that was the reason why they just didn't really get it. So from that period on, there was an opportunity for really quite sophisticated science understanding and modelling to reach young minds. Very, very exciting.
Yeah, that sounds really, really cool. And in your own, so then in the end, like, how did you decide that teaching is for you when you wanted to become a teacher? Like, how did that come about?
I think I stumbled into teaching. I just continued doing science at university. I did a chemistry and major and did some physics and psychology and stuff like that.
Cool.
And then at the end of the degree, what do you do? Well, I just wasn't really thoughtful about it when I was going through, and teaching just seemed, I think it was actually a natural teacher anyway, and I just landed in that spot.
Yeah. So did you have to back then do a special teacher training, or were you like you did science and then you decided to further on your education?
Yes. So what happened then is you did a degree in science, and then you did a diploma or an extension degree in teaching, which I think is a better model than doing a science education, 4-year science education degree.
Right.
Because you get a much deeper understanding of the science principles in the other way. And really a lot of the teaching practice and skill comes from being in the classroom, and you just become a better teacher over time. I think that's what happens. So it's very valuable if you have a deep understanding of the science to start with.
Yes, it's much more comfortable also to be able to share that information if you understand it.
Yeah.
So in terms of like once you became a teacher, what was it like? What were the aspects that you enjoyed the most, the ones that you didn't, and how would you change things now if you were back in the classroom?
I wasn't a maverick in any way. I just taught. I really enjoyed the subjects. I loved the science of it, and I enjoyed sharing it with young, growing minds. And so I gravitated to year 11 and 12, just teaching that level, because there was a lot of kind of intellectual pleasure in doing that. So, and in a way I avoided the challenge of a lot of teaching, pedagogical challenges that you get with younger kids. So, that difficult 13, 14, 15-year-old period.
They're kind of trained by that age when you got them.
Yeah, they were, and they self-selected to be there.
True.
And so I had a kind of a sweet run of that. But I end up also developing a lot of relatively advanced ways of explaining difficult concepts. Because when you repeat it so many times from so many different angles, you get good at it. Just like you get good at anything if you do it often enough. So I didn't want to become go into administration, become a deputy principal or a head of science. It just wasn't.
Yeah.
The administration was completely.
Not your thing.
Well, it was against my thing, really. I just didn't. I disenjoyed it rather than enjoyed it. Yeah.
What were the things that you found that kids loved the most? Like, what were the aspects that you remember that they enjoyed so much more, other than, because I know like exams are frightening and all this, like we've got to learn, we've got to do the HSC, like, or whatever it is, the prep for the final exam. Like what is what was the aspects that you thought, wow, kids really dig this, like they really love this part of, learning about chemistry?
Well, with 16, 17-year-old kids, it's a combination of, obviously doing pracs is hands-on stuff is really engaging, but also the elegance of theory. When you can couple it with that is also very satisfying for both the teacher and the student. Hello, crow. We were talking about crows earlier.
What was it that you did before?
Clap the crows.
A bit of science happening.
Yeah. Instead of stone the crows.
See, it works. You're so right.
Yeah.
Loved the practical engagement. And then, did you retire? Or did you? What was next sequence?
What I was saying was that they enjoyed the practical engagement, but the older kids also enjoyed the theory. Like, if there's something incredibly satisfying about explaining a phenomenon from using an abstract theoretical model or a mathematical model or something like that, and seeing how it the real world mimics this, or vice versa. So, but that was more. That's why I gravitated towards year 11 and 12 kids. But primary school is the other end, of course, and you would almost expect them to be completely just obsessed with a hands-on engagement. But that's the thing that I discovered, was that actually wasn't the case, that young kids could understand the modelling as well, and that it also had a multiplier effect on their enjoyment and engagement. It wasn't just playing and hands-on things and seeing and feeling and touching. It was the understanding, the cognitive development.
Yeah, and this is in children that are at preschool level. You're even talking
from
about,
kindergarten,
right? Kindergarten onwards.
Yeah.
Wow.
So we've dramatically and profoundly underestimated their capacity to think abstractly. Actually, like everybody, Jerome Bruner is a famous educational theorist, and I'm a kind of follow his principles. He was saying that everybody, even adults, need to start with the concrete level of understanding, the hands-on, and we all go through a sequence through to what he calls a pictorial understanding, and then an abstract understanding of concepts. So that's true of adults and also of children. So whereas what we've kind of done is we've said, okay, that kids can only do the concrete stuff, and adults are kind of live in the abstract world. But we
the other way around.
We both live in both. You know, kids and adults live in both a concrete and an abstract
And
sequence.
it makes sense, because even a baby learns first by observing, by making sense of something, and then trying it out.
Then trying it out.
And whether it's through...
And then they build mental models
Yes.
for and start predicting, and it's the same sequence.
Yeah, and then problem solving and all of those things. And it does just start off exactly in makes total sense.
When you think about it, the kids are already doing the concrete, like they're throwing balls in the playground. A ball is a spherical thing that rebounds when it hits a surface. That's what an atom is, just on a microscopic level. So the only difference is really scale.
Wow.
And kids can go scale so quickly. There's no barrier for a child to think. Well, they've Dr. Seuss has written books about that. You know, the Whoville, this invisibly tiny village of young people. Well, not young people, of small people, that children can imagine so quickly. So what we've been doing in primary school is capping their learning to the concrete and the level of the senses, what they can feel and see and touch. And then that's it. You're not given any opportunity to take it beyond that. Whereas if you can give them, the only way you can see an atom is through your imagination. So if you give them and children can imagine.
Yes.
So once you give them the opportunity to imagine an atom and a molecule and a chemical reaction and all of the other elegant things that this huge microscopic world that is around us, then they're not walled into their classroom anymore. There's a kind of a freedom that primary school kids can enjoy that they don't otherwise have, and that's one of the reasons why they love it so much. And that's what we're finding, is that primary school kids not only understand this stuff, but they really love it, and their enthusiasm is they're crawling up the walls with enthusiasm.
That's so beautiful.
Yeah.
Ian, how do we lose that? Like, what happens, do you think, where these children, what causes kids to shut down like that? This imagination, this ferocious appetite for learning and experimenting and being so inquisitive. What happens to us? Why aren't we all still like that?
Well, I think if you're not allowed to imagine, if the curriculum sort of prescribes that you can't go into that imaginative world of building mental models, which is what science is a lot about, then it's like a muscle. You don't exercise it, and by the time you've arrived at high school, you're just stuck at the concrete level, and that is ultimately boring. You know, like humans need imagination, and they need stories. They need a narrative, and science can provide all of that. It's got its own narrative. It's the best story ever told.
Yeah, the story of the universe and the reality, story of reality, the only concrete reality actually that exists.
It like the children are just gobsmacked with the, like there's it is so much better than fiction.
It is.
This story, yeah.
Yeah, it's beautiful. Yeah. And when did you actually start working with younger children? Did you retire first and then, like, how did it happen?
Yeah, well, I reached my kind of end point of classroom teaching. I taught it so many times. I was really good at it. I could just walk into a classroom. I knew how to flow through a set of concepts in the right sequence and elaborate it and bring the students along with the journey. But I was doing the same story every time. It's like reading the same story. So I retired from teaching and started another business in adventure tourism. So what does a science teacher do when a chemistry teacher do when he retires? He either chooses to make methamphetamine.
Great, all your teachers out there.
Like, as in, you know...
your future path.
Yeah, or he becomes an adventure tourism operator.
Wow.
So I started taking international students and backpackers to sort of fun places like...
That sounds amazing.
Yeah, so that was sort of a 10-year journey.
Did you still introduce chemistry into that?
I did, actually. Yeah. Well, a lot of astronomy, you'd sort of stand out under the stars, and you could say that light that we're seeing now left, you know, 4.2 years ago, and we're just seeing what that star was like 4.2 years ago. And the kids were... And it was really true, you know. That's the fun part about it. Yeah. So I threaded a lot of science into the
so fascinating. Must be great.
But then the problem with doing something that you love as a business is that it turns into a business rather than something you love. And so I sold the business, and that was when I think Tom was he was about 3 or 4, and then when he was about 7. That was when that conversation happened in a park, where he said, basically, "What's the world made of, Dad?" And as I say, you should never ask a chemistry teacher that question because you might get the long answer.
Yeah, that's cool. It's cool that he had that interest.
Yeah, well, not only that, but he was able to, like, the answers were followed by more penetrating questions from his side, and so it was very clear that he was able to grasp that the world was made of this vast microscopic dancing of particles that were joining and separating, and so it was. And he'd ask really kind of left of centre questions like, you know, "Dad, what happens if an electron, you know, gets captured by a proton?" And because the electrons go around the nucleus, the protons, and that is actually a very good question, and it does sometimes happen in a neutron star. The gravity crushes an atom, and so you end up getting all these neutrons. So he actually preempted that that question.
That's so incredible.
Yeah,
that's what kids have. The fact that they're using their logic and their experience leads to all these very, very intelligent questions if they're allowed to ask them.
Yes, that's right.
And I feel like it's just not like, you know, just these, even that question, but why, always leads to something that needs to be explained further. So they're very, very inquisitive, and I think this is where we, as adults, need to keep going with that. Keep asking about
it's
why.
Funny. There's something about the why questions, because the why questions are very, very fruitful, but they're also very exhausting for parents. And so there were times when I'd just say, "Look, Tom, you're only allowed to have 5 Ys per day. And on the weekends, you can have 10.
Instead of lollies, you give them Y questions.
Y questions.
And so you've got scientists brewing in the...
So you've got to be very careful with your Ys. You know, you've got to make sure you frame the question very well. You can't waste them.
Yeah, don't waste your Ys.
Don't waste your Ys.
Don't just say them for the sake of asking. So then when did Atomic School start into, how was that born?
Well, after that conversation that where Tom asked the fateful question, what's the world made of? I realised that he could understand basically at a high school level, even though he was 7, I suppose grade 2. Mm-hmm. So I went to his class at Ithaca Creek State School and tested out whether they could also follow these ideas, and they could. Yeah, it wasn't just that Tom was, well, of course Tom is special,
as we all are.
As we all are, yeah. But his whole cohort could just jumped on board and went as fast as Tom did. So, and that's when I started developing a curriculum and a whole set of pedagogies that might sort of transfer the way science was taught in high school into those concepts, but into a primary school setting, so that all of the constraints of a primary school classroom. There's that crow again. So excuse me, do you mind if I? Okay, we can continue now. Yeah, see, it's gone.
Bye. There's another one.
Oh no, it's the same one.
Oh, is it?
Anyway, so I had to develop all of these sort of different materials.
It's just like they do it on purpose.
Yeah, no, they know we're having an interview. So I developed all of these hands-on materials and lesson plans, and in fact, one of them has become was quite innovative, and I've patented it.
Wow!
It's a little magnetic. They're little atoms that have magnetic tips on them, and so the chemical bonds can form spontaneously, and they're much more a realistic way of and much more fun way of making molecules out of atoms. So
that sounds awesome. So by developing this, you allowed children to have this tactile understanding of what it's like to be an atom, what it's like to handle an atom, and
starting
how
off with the concrete, and then building up the principles from that, from the concrete to the abstract, and then they could run just as fast as high school kids could. And so we've really that means we've got an opportunity as educators and as a society to introduce this learning much earlier, and allow them to internalise these concepts and this new language much earlier. It's a little bit like an alphabet, like the periodic table's like an alphabet. It's a whole lot of letters. And in the same way that you can put letters together to make words, you can put these symbols together to make compounds or molecules. And whereas the alphabet and words can make sentences and build up literature, all of these chemical combinations form the physical world that we're living in. It's sort of like a book.
It's like the language of life.
It is, yeah, like of existence, incredible. Of the universe.
Yeah.
So it's a big deal, like if we can get this to be threaded into kids' understanding and lives much earlier, so that it becomes a part of their, it becomes a, like intellectual capital that they just bring through to high school. So that then we can start from a much higher level at high school.
Yeah.
And also, of course, famously, where kids are getting bored in high school because it's the wrong age actually to teach them. So if they arrive and they're already fluent in science,
Yes.
fluent in this language, then we don't lose them,
Yes.
and we can produce a lot more. I call them scientific Mozarts.
Yeah, and because it's that disconnect between not having that background early, like with all the other things that we do with maths and other things like language, and without having that scientific sort of foundation, it must be very disengaging for students, you know. And I feel the same way, like I've had those experiences as well, and it's really traumatizing because you know there's something so incredible in it and you just don't get it, and it's really
it's hieroglyphics.
sad. Yeah.
So rather than being a sentence that you can read, it's a whole lot. It's like being dyslexic, I think. You know, it's all of these hieroglyphics that don't make sense, and so you become there's a kind of you're repelled by it. There's an aversion to
It's
it
scary.
rather
Yeah.
than being an attraction to it, which it really should be.
Yeah, and it also feels not only scary but also overwhelming. Like, how am I going to get this? You feel dumb. Like, all these emotions come up as a result of this a kind of an unnatural introduction of it at that late stage.
It's really scrambled introduction too. It's really introduced in a strangely disconnected way, and too fast. Like, you don't teach them anything up until grade 6, and then from grade 7, 8, 9, 10, you cram in all of this stuff that in a really disjointed sequence, and we're setting up our kids to fail.
So why is that being, like, why is this happening? I mean, obviously there are teachers. I'm not sure who the people that have designed the curriculum curriculum.
Who are you?
Yeah, like what? Because, you know, and also I'd be asking the children. Like, I'd be interviewing children, asking, like, why is this difficult for you? They might come up with answers where it's an easy transition to something that's, as you say, meaningful for them and approachable and earlier, and so that future children don't have to go through this trauma.
Well, that's our goal, is to introduce atomic theory. Like I think Ruben said, was that children have a human right to know about atoms from an early
human
age.
rights issue.
Yeah, that's right. It's a human rights issue. So it's a form of human rights abuse to not teach them this from an early age.
It feels like it.
It is, yeah.
Yeah.
And not only just atoms, also there are a few other key things like Newton's laws of motion
exactly.
and forces.
I was going to say.
They're kind of if you think of it as a tree, they're the trunk concepts.
Yeah.
And then as the tree elaborates and becomes branches and leaves, you get all of these derivative topics that everything is that sort of.
It's kind of building upon those foundations
Yes.
that are so key to actually learning everything else almost.
So that's sort of like they're the ancestral parents of all of these, of the whole of the science. And we need to get in early. But we're just completely underestimating children.
Their intelligence,
their
inherent intelligence. And I think also, like, so in a sense, like, you're doing that already with Atomic School, because you've got a YouTube channel with just all this amazing stuff that you can learn about atoms and the language of the universe. How else are you doing that? Physically going to schools?
Yes, that too. Yeah, we're trying to recruit schools, and any school, any parent or teacher or principal of a school, or Director General of the Department of Education, or any person in a CARA who's listening, then we would like to collaborate with them to build. And we've got so much experience now, 10 years of living experience in classrooms, of knowing how this students respond to all of these different ways of teaching it. So we're trying to get it into classrooms, and we're also trying to get teachers. We're not only providing this understanding for students, but also for primary school teachers, trying to make it easy for them to deliver it to their classes.
Wonderful.
So that's why the videos are so useful. It's because they do a lot of the heavy lifting in terms of explanatory things with animations and narration. And we've got click and teach lessons where
Wow.
teachers can sort of stop at certain points, and then there can be a class discussion. And the teachers don't need to be pretend that they're experts in science. They can just take these lesson plans that we've developed, and even one of the students in the class could do it and teach it to the rest of the class. So the whole thing
Wow.
is a sort of like it is designed as a self-learning
Beautiful.
design,
Yeah.
and we've found that after teachers have taught it a few times, they become more confident, and then they become more independent, and then they can start to relate this new understanding to other areas of their learning,
Of course.
like geography or English or other languages and
Biology
so
and
biology.
everything,
Of course, everything is all these cross links that
Yeah.
that enrich and deepen. And it, for example, when students start to understand what an H2O molecule is, then and an O2 molecule that we're breathing, then they can understand, and a CO2 molecule.
Yeah.
All of these things are just like the kids build these molecules in grade 1 or 2.
Yeah.
Then they can understand how respiration and photosynthesis, instead of just learning that photosynthesis is like the word equation, they can
Yeah.
actually see the molecular models and how they, as Ruben has developed this really well, is how in the case of photosynthesis, how the water from the soil comes up and the H2O molecules get zapped with photons of light and combine with the carbon dioxide from the air
Yeah.
and build a sugar molecule.
Yeah.
So all of that becomes within easy reach
Yeah.
of primary school kids, rather than this airy-fairy kind of fobbing off and the baby science that we're teaching them instead.
Yeah.
So
Because they're capable.
they're capable.
They're capable and they're hungry for
Don't
it. And
patronise the. Don't patronise them.
Yeah, exactly. And I often think also teaching any concepts of science, when I work with kids, in nature, oftentimes I won't dumb it down. I don't feel there's a need.
No,
You don't
there
have
isn't.
to make
No.
it, strip it down to bare essentials. You can actually say it, and if they don't understand something, they will let you know.
Yeah. Yep.
And I find that that's another aspect where, as adults, we think if we don't know something, it's really hard to learn, and we don't ask the questions. We become very stifled in this inquisitive nature that all human beings have, and we need to embrace it and keep going with it.
Yeah.
And
Feed it.
yes,
Yeah.
feed it the right food,
Yeah.
which is
Yeah.
this amazing way that you're
Yeah.
teaching, from the bottom up rather than from here somewhere to.
So our goal is that every primary or elementary school student in the world should be have the ability to learn about atoms from kindergarten, and also the parallel subjects in physics and biology and earth and space science.
Yes.
But we've really sort of done a lot of the heavy lifting with developing the pedagogy and curriculum sequences for atomic theory.
Yeah.
So that's sort of really ready to go for any student or school that wants to take this up. They can contact us, and we
Great.
will support them in their implementation in their school. Support their teachers and also with lesson plans, with materials. With videos
Great.
and the full caboodle.
Yeah, that sounds great, and definitely we're going to promote that
Good.
that thing, because I think it's just such a worthwhile thing to have for the rest of generations to come.
Well, I think it's civilizational
Yes.
in its impact. Like if you think what does learning language do for humanity? What impact does that have on civilization? Well, this is similar.
It's astronomical, really, isn't it?
Well, literally.
Yeah, literally astronomical.
Yeah.
Atomically astronomical. That sounds awesome. Look, I just want to go on YouTube right now and I've already looked at some of them, but I want to do the whole sequence from bottom up, because even when you're learning chemistry in high school and thereafter, and physics as well, it's you still don't really get it. That's what I feel, because those foundations have not been there from that early childhood.
Yeah,
and I feel like
that's true.
it's very complex and hard, but
and missing one little step, one gap, means that sometimes you get arrested at that level, and you can't take it any further. And so what happens is that people kind of understand that there's a gap there, and so they just stop it at that point, and they never take the explanation to the next level.
Yeah.
And you see a lot of that on TV, on sort of science programs on TV, where it sort of gets up to a certain level of detail and complexity, and then it goes all airy-fairy, and it becomes the science becomes very soft.
So Ian, I'm really interested. Did you bring your sticky atoms with you today?
Oh no!
Oh.
Yes, I did.
I want to.
I thought you'd never ask. Yeah. So these are the sticky atoms, and they've just been approved by the US Patent Office as an invention, which is a big deal. And if you take one of them out, the red one represents oxygen.
Great.
Oxygen atoms aren't actually red, and they're not. Real atoms aren't made of plastic. These are just models.
Fair enough.
We talked about this with the kids.
And they're a bit smaller as well, aren't they?
They're a bit smaller, like 1 billion times smaller. So the kids pick that up just like that. They know already. So there's a lot of criticism that we're teaching them that oxygen atoms are red, for example. So they understand that these are just representations.
So which ones are the hydrogens?
The white ones.
Ooh.
Okay. So what makes these innovative or inventive is that the tips of them have bipolar magnets in here, or two poles of a magnet, so that when you bring up another atom, then they join together to form a chemical bond. But it doesn't matter which angle you bring it up; it'll always just spin around and adjust. Yes.
Wow.
So, and that's what chemical bonds do. They don't. They will spontaneously form. So you don't have to. And the other kind of atoms that models of atoms are called Moly Mods, which are very good. But they use little plastic lugs that you insert.
Yep.
And but what's good about these is that you don't actually have to force them to make them go. Yeah, that Mickey Mouse atoms. Yeah,
so
Mickey Mouse molecules, the kids call them. So they just happen spontaneously, and also you need a bit of effort to pull them apart, and you also need effort to pull a real chemical bond apart too. So the energy relationships are well represented with this, because the magnetic forces mimic the electrostatic forces with chemical bonds. So that's what makes them theoretically superior, as well as being more fun.
Yeah.
So how good is that?
So did I just make water?
You just made water, H2O.
Yay!
So that's a.
And if you make more of them, if you wanted to make like a larger molecule?
Well, if the black one is a good one.
Because it's got many bonds.
It's got 4 bonds. So that is a carbon atom. Represents a carbon atom. So that means that it's much easier to make
hydrogens or oxygen.
Yeah, we can put all sorts of atoms together and build them, and also we can make a double bond.
Oh wow!
Which is really cool.
That is incredible. So you literally can make molecules.
Yeah. And the double bonds are as easy to make as a single bond, and they're spontaneous.
Cool.
So we've made a real molecule here.
Yeah. Whoops.
And we get the kids to build all of the really important molecules in their lives, like O2. O2, of course, this is the one that we breathe. It's an oxygen atom, double bonded to another oxygen atom. And the kid, right from grade 1, the students learn that oxygen is O2, and that it's a double bond. They don't even
remember how it looks.
Yeah,
as well.
they don't think twice about it. It's just an early introduction. And also they know that water molecules are bent. That's their shape. And being bent, the fact that water is bent is a really important feature, because it means that water is a polar molecule. And that means that other water molecules are attracted to it, which means that water is a liquid instead of being a gas. So all of these things thread together and build. Like, we don't have to tell them that in grade one. This is quite like intermolecular forces, and it's quite an advanced topic. But they already know that they don't have to learn that water is a bent molecule, because they just know that straight away. By the time they get to grade 6 and they learn about intermolecular forces, then the fact that this is a bent molecule is just, everybody knows that. And also carbon dioxide is, when they build carbon dioxide, carbon, that's a double bond to one oxygen, and a double to another oxygen. Now, what shape is that? Is that bent or triangular, or what? It's straight.
Yeah, I was going to say it's a straight.
It's a straight molecule,
Yeah.
and the fact that CO2 is a straight molecule is really important. That's one of the reasons why it's a gas at room temperature. It's one of the reasons why that makes it problematic, but also makes it, it's just one of the linkage. There's another one, for example. Air is made of O2, but also nitrogen. This is a nitrogen atom. Two nitrogen atoms come together, and they bond with each other 3 times to form a triple bond. These are new, so they're a bit stiff. But that means that this is an N2 molecule.
Wow.
Now, the N2 molecule is 80% of the air that we're breathing is N2.
And we don't even talk about it much at all.
No.
One talks about nitrogen.
Poor old nitrogen.
Yeah.
But the fact that it's got a triple bond, means that it's very stable. It's very hard to pull it apart. And that's why it doesn't get, when it goes into your lungs, it doesn't bond to your surface of your lungs. It just comes out as N2 again. So it's an inert gas in terms of, and that's a really important property of N2, because otherwise, if you had nitrogen, if these were easy to pull apart and they stuck to atoms in your lungs, that could be a problem.
So is that similar to what happens with nitrogen poisoning? Like when you do diving and stuff, look what happens there?
Well, with nitrogen poisoning, the N2 molecule doesn't actually
come apart or anything.
No,
it's just too much of it.
It dissolves into your blood.
That's
it becomes a solution. So that's a physical change rather than a chemical one. So it's the fact it's really hard to pull this guy apart. And
a lot of energy would be required.
Yeah, and that's why, for example, that plants need nitrogen for. We need nitrogen to make protein. So one of the challenges for science and humans is to turn the nitrogen that's in that form into a nitrogen, pulling it apart and putting it into a protein form, into a nitrate, or a bound form, a fixed form, it's been described. So that's what a lot of plants are able to do that, or bacteria in the soil. They're a nitrogen fixing bacteria. You've heard of that. So their special ability is to break apart the N2 and to form nitrogen atoms that then go on to form useful molecules that we can then use in our bodies to build proteins.
So amino acids and proteins.
Amino acids, So
great. That's such fun way to look at life when you start playing with little balls.
Yeah, and the last really important molecule is this one here.
Nitrogen and 3 hydrogens. Ammonia?
Ammonia, NH3.
Yeah.
So when you say amino acid, the amino is related to the word ammonia. So it's chemically related. So all of these things just like they feather together, all of these ideas.
And so relatable to us as human life or plant life.
This is one of the molecules of life. And so the methane is also another with the CH4. So that this molecule, we teach them the 4 magic molecules, which is H2O, NH3, and CH4 and H2, because they're kind of the building blocks of things.
Yes.
So this is a methane. This is the molecule that that it's a coal seam gas. It's also called natural gas, and it's used to as a fuel for driving buses. So powered by natural gas. It's also the fuel that comes out of a gas stove
and cows'
bottoms. And they burp it out as well.
They burp
it and fart
belch,
it out.
Yeah. And so because it's so much more potent than carbon dioxide as a warming gas of the atmosphere. Is it because of the bonds?
It is. It's because of the bond strengths. Yeah. What happens is that it's only got a single bond, so it vibrates more at a different frequency. So that when the radiation that's coming into the Earth hits the surface of the Earth and then comes out as infrared. So it comes in as light and UV and so on, and then it comes out as infrared, which is longer, and that tends to be the same frequency of vibration as the vibration of backwards and forwards vibration of these atoms, and they absorb it. So they because it's a resonance frequency match, so they absorb that frequency, and then that becomes more energized and becomes hotter, basically.
Yeah.
So that's why the globe is warming, is because these molecules, CO2 does it as well, but CO2's got a double bond, so its frequency is higher, so it doesn't have the same, it doesn't match the same frequencies that are escaping. So that's why this one is a more potent one.
Yeah.
But it also means it's also more unstable because they're only single bonds.
That's right, yeah.
These are all just from very primitive stuff. The fact that this is a single bond means that this can be pulled off more easily. And so methane, when it floats around, it breaks apart more easily. So although it's a more potent greenhouse gas, it doesn't stick around for very long. It tends to oxidize. So this will go off and join with some oxygens, form a water molecule. And this will go off and, this might become a carbon dioxide or something like that. So all of these quite really advanced concepts are threaded back to stuff that they can learn in grade 1.
It's fantastic. Fantastic. I want to go and be
Why aren't we doing it?
Let's do it. Let's do it.
It's so easy too. And the kids love it.
Yeah.
And the teachers can do it. We've got teachers who are not trained as science teachers who have picked up with this and run with it without any problems.
Yeah.
I mean, it does take a little bit of
learning.
Yeah, but everything is there for them. The resources are there, and it's also interesting for them too.
Yeah, absolutely. And you can even spin this into English or maths as well so easily because you can count and and you can name new things like oxygen is a word. There's so much you could do. You could write poems about it if you wanted to. So there's just so much application with it.
And the word meth, meth has got a lot of street cred, hasn't it? I sell meth or something like that as being a what do you do for a living? I sell meth, I'm a meth head or whatever it is. All of these kind of backstreet language comes from the word methane. It's sort of like it all is related, and
it's crazy.
Yeah.
That's when you start seeing the threads of likeness between everything in nature, is because we're made out of those same atoms, so we're always going to find similarities.
The geometry, the geometry and the grammar of that had a little bit of blood in it, so it must have bitten one of you guys because I haven't been bitten yet.
Oh really?
No.
Must be the meth in your blood.
It must be the meth in my blood, or maybe it's this meth molecule.
Well, yes. Look, this is fun stuff. I love it, and I really think I want to play more with that. So we're gonna
We'll go away and play.
we'll go away and play. Thanks for listening, guys. I hope you enjoyed us talking about sticky molecules. Sorry, sticky
molecules. Yeah.
Sticky atoms making
yeah.
molecules.
Yes.
Thanks
Okay.
so much, Ian. That was
Thank you,
really
Sandra.
fun.
Great. I talk too much.
It's all good. That's what we need to do to
Okay.
understand things.
Okay.